So I should say it's really a pleasure to be here and give this first lecture course. Kind of started out running a bit in the morning, but it's worthwhile to say that. Thanks all for being here. Now I'd like to tell you what I'd like to cover in the second lecture. Basically, the goal is up there. I showed you this amazing one-line formula from 1986, and thanks to some of these new ideas that I hinted at, nowadays it's actually rather easy, with the right tools, to prove such a formula. And time permitting, my plan for this lecture is to give you the basic tools for doing that, so that ideally, if you have a bit of free time, you could see that for yourself, and we can discuss it tomorrow morning. Now, to get there, there's a first bit where I have to talk a bit about the organization of the amplitude. We already covered many parts of it, the helicity and how to deal with the momenta, but I still need to tell you about the color. And in fact, we had a question earlier about some aspect of that. So how do you deal with the fact that gluons are, that we have a gauge group SUN and that the gluons are joint particles in that gauge group. So I'll first tell you how we deal with that, and then in the main bulk of the lecture, I'll tell you about a method for computing tree-level amplitudes recursively. And this will be a completely general method. And then with that recursion, you will be able to prove by induction that this formula for the MHV amplitude is correct. So let's start with the, I call it color management. Color management of the amplitude. So again, the idea is that amplitudes depend on so many different things. It's good to organize a little bit and then have kind of smaller pieces like this one up there, which just depends on the kinematics, so we can forget about the color. So the gluons, as I said, they're in the adjoint representation of SUN. Sometimes, for conceptual reasons, it can also be useful to consider UN instead of SUN. If you think about it, it actually does not change very much. It just can be convenient. Basically, you're adding a photon, a diagonal element, by doing so. And in fact, at tree level, it does not change anything because, as you may know, just photons they don't couple directly. They need some fermions to couple to form couple through loops, for instance. So if you just have a tree-level amplitudes of only external photons, it will just vanish. Or the same goes for any number of photons and gluons. But anyway, so now how do we deal with that color information? So each gluon will have an index, a joint color index. And that runs from 1 to n squared minus 1. Of course, in QCD, n is equal to 3, and there's 8 of the gluons. And then we need the generators of SUN in the fundamental representation. So these are traceless Hermitian matrices. N times n matrices. So we denote them by T, TA. So n squared minus 1 such matrices, and they have fundamental indices I and j that run from 1 to n. Just a bit of notation for this SUN. It's a normalization condition that you take the trace of two such matrices, and this is delta AB. So depending on what convention you use, you might have something else here, but that's what we can use. And as far as the algebra is concerned, we take the commutator. So the commutator is going to be basically the structure constants of SUN times the number generator. And in my convention here, there's an I square root of 2 in this relation. I think essentially this helps remove some other factors of root 2 elsewhere in the amplitudes. So this is again, this is purely conventional. Now let me just remind you of the Feynman rules, but only from the point of view of this SUN. So if you have a propagator, so then for each gluon we have it's a joint index, and the propagator is proportional to delta AB. So that's simple. And then we have the vertices, for instance, the free gluon vertex ABC, and this is just proportional to the structure constant FABC. And likewise for the four gluon vertex CD, we have that this is given in terms of structure constant as well, where here there's a sum over one of the indices. So this is just schematically how this looks like. Right, and so now the goal is the following. We want to think about these Feynman rules and identify all possible color structures that can appear, and write down some basis for them. So in this way we will have dealt with the color information, and then the coefficients in that color basis, that will be things that only depend on the other quantum numbers, so helicity and depend on the particle momenta, but no longer refer to the color. And so then we'll, and this is an example of that, in fact, and then we can just focus on that entirely, forget about the color, and derive rules for computing these coefficient amplitudes. So as you can see by the Feynman rules, everything, so if you think about a given Feynman diagram, it will be expressed in terms of these structure constants. And now there's the following strategy that we're going to follow. We first take these structure constants and instead rewrite the expression in terms of the generators T. And to do that, we can use these two relations. Essentially, saying that, so if you take that relation, multiply by some TD on both sides, and then take the trace, we can isolate the structure constant. So in this way, we can rewrite this, saying that FABC is I over root 2, and bracket trace of TA, TB, TC minus trace TA, TC, TB. So here I've written out explicitly the commutator. So if we do that, then and we now apply this identity to any of the FABCs in our Feynman diagram, then it's clear that any Feynman diagram will be expressed as a product of such traces. Right? So we have any Feynman diagram. It will look like so. Some trace A, and well, two things could happen. So sometimes you see that we have external indices, so then these will just correspond to the external adjoint indices of the gluons. But sometimes we can also have contractions like here, and so then this will correspond to indices of the T's here, which can be contracted between different traces. So So for instance, something like this, and so on. There can be many such traces. Just pieces. So the main point here is that this is a completely systematic step. You can always do this. You can program it on a computer. So completely general. So now, so I told you that we have these contractions between indices that, for instance, come about when you have a propagator. So now this allows us to simplify the expressions, and so this we can use the completeness relation of the for SUN. SUN will be for UN. So this tells us the following: this when we sum over all the generators with indices I1, J1, indices I2, J2, we get the following: delta I1, J2, delta I2, J1, minus 1 over n delta I1, J1, delta I2, J2. So this relation expresses the fact that we have a complete set of traceless permission n by n matrices, and in particular here the second term it implements the tracelessness condition. So you can check that when you take the trace here, that thanks to this term you get 0. Similarly, you could do the same thing, and this is in a way is a bit easier for not for SUN but for UN. And then in this case, you would not have this second term here. And as I told you earlier, as far as tree-level amplitudes are concerned, I mean, there's no difference because the photons decouple anyway at tree level. So if you're looking for a shortcut for doing this analysis at tree level, you can really just forget about this term. So now next, basically we use this identity to systematically get rid of the products here. And as I just argued, we can just forget about this term. So when you now imagine applying this to a product of two traces where there's a joint index connected, then it will just basically merge the two traces together and make it a single trace. Right, and we can just iterate this process. Now, so iterate this to eliminate all contractions. I have an example here, but I think in the interest of time, I'll skip it and just give you the result now for tree level. If you wish, then we can. It's probably a good exercise to do it in an example and see what happens to these traces. For instance, for given 4-particle Feynman diagram. What I'm saying here, it's valid for any Feynman diagram. So it's you could take any example you like to check this. So the option is the following. So we arrive at the polar decomposition for amplitudes. And I'm going to quote the result for specifically now for tree-level amplitudes. So let's say for an n-gluon tree amplitude. So I denote the full amplitude, including the color information, by some curly A. Tree, so that it's clear that it applies to that case. And let me put here just all the let me just put here explicitly what the amplitude depends on. So we have the momenta, the helicities, and the color information. And now we can write this as the following. So we get a sum. And it turns out that at tree level, after this process, you can only have single traces. So although at intermediate stages you have many traces, thanks to this identity, the traces merge, and you just have single traces, but for different orderings of generators. And so one can write them in this way. So we have A, and then some permutation of 1. So here we'll have a sum over different permutations. A sigma of 2, and so on. T A sigma of n. And then that multiplies something that we call a partial amplitude. And this partial amplitude now just depends on the remaining information. So well, I think I'll just label it sigma 1 to sigma n, and where each of these of course depends on the momenta and the helicities of the corresponding gluon. And so there's just some two things missing. By convention, I'll put the coupling constant here, because it's by engineering a tree-level amplitude will have this power of loop momentum. So I prefer to put this here. And I also need to tell you what this sum goes over. In principle, you could write this formula saying that sigma are actually all the permutations. But this trace here has some cyclic symmetry, so it makes sense to divide out that cyclic symmetry. And so these permutations that we need here are just all permutations of n particles, but modding out over cyclic permutations. So again, so these then we'll call partial amplitudes. So a couple of comments. I told you this is the general formula at tree level. You can go through the same argument at loop level, where the difference would be that you can not only have single traces, but also multiple traces. So there's a generalization of this formula where you'd have another term also with double traces, and in general multiple traces. But as far as we're concerned, for tree level, this is enough. And now this is very useful because it just tells us how we can in general write the color information, and then from that point on, it's sufficient to compute these partial amplitudes. So in fact, once we know this partial amplitude here, then the formula just gives us the whole information. So from this moment on, we can forget about the color. Now, there's a second very important point, which was actually subject to a question earlier, that it turns out that in this partial amplitude here, so we have a particular ordering of the gluons, and so that for this reason, these partial amplitudes are also sometimes called color ordered. So so this color ordering is quite important. If one thinks about this, where these, so one can think now what contributes to these color ordered amplitudes. I'm thinking how I want to say this. So the important point is that thanks to this decomposition, we have some additional properties of these color-ordered amplitudes, namely that they can no longer have singularities in any place. So a generic amplitude can have singularities as any of the momenta, let's say pi and pj, become collinear. But for these partial ordered amplitudes, this is no longer true. The only singularities are when a sum of adjacent momenta becomes collinear, or the sum of adjacent momenta, the square if that vanishes. So these are the simpler singularity structure. So color ordered amplitudes have a simpler singularity. So concretely, so if you have such an AN3, so now this again, this A here, as opposed to the curly A, this refers to the color ordered amplitudes. So if you have such an amplitude, then it will have singularities only for at locations where you have some momentum, pi plus 1 and so on. So a sum of adjacent, what is some j? Some sum of adjacent momenta vanishes. And so this is different from the case here, where of course when you take this and sum over all also non-cyclic permutations, you get a whole set of possible singularities. Okay, so now there's in fact a lot more one can say here, and I think I want to move on to this topic of the recursion relation. So I would just say the most important things that we need for that. But let me say that thanks to this idea of color organization, one can now define an improved way of computing these partial amplitudes. And in a way, this comment I just made is actually simpler to understand if one goes through this. So the point is that in the initial Feynman diagrams, you have the color information, you have the FABCs and so on. Now, through this process of defining the partial amplitudes, you can also arrive at let's say some effective Feynman diagrams, so-called color-stripped Feynman diagrams, which essentially are very similar to the diagrams we had initially, but just with no FABCs. And then in this new color-stripped formalism, there's you can directly draw Feynman diagrams contributing to each of the partial amplitudes. And there are all these amplitudes that you're supposed to draw are just planar tree-level amplitudes. So in this way, in these new rules for computing the partial amplitudes, this property is also completely clear. And you could say, well, practically speaking, this is of course a better way of organizing the calculation, as opposed to writing down all Feynman diagrams with the whole color information. You just immediately use this knowledge of the decomposition and directly write down the effective Feynman rules, these color strip Feynman rules, for defining the partial amplitudes. So this is, of course, a very, very good way of proceeding. Now, why am I not discussing it, or why am I not discussing it in more detail, is that I'd like to even bypass this step, saying that with development of new ideas, sometimes we don't even need the Feynman diagrams anymore. And in fact, we'll see a way of computing this MHV formula for all number of particles n that I had earlier without actually going through this color ordered Feynman diagrams. So for this, in this sense, if you wish, it's a useful, very useful tool. And if you want to reproduce some of the results we have, let's say for 4 particles, in general low number of particles, then this is certainly something very good and a good exercise. But we won't need it now for this goal of computing the endpoint formulas. So, so this reason I'm going to skip it, but I'll just mention this is something interesting to read up. So more details. For more details, you can look at the color ordered Feynman rules. And I think this is nicely reviewed in some reviews by David Kosovo and his friends, and I think we also have a discussion of this in the lecture notes that was in the book that was advertised earlier. Any questions at this point? All right. So then I'd like to continue with the recursion relations. So these partial amplitudes is what we'd like to consider. Let me show you a very nice, conceptually nice, and also practically a very useful way of computing them. So these are the BCFW recursion relations. So this is Rolf Brito, Freddy Cacciazzo, Bo Feng, and Edward Whitten. And something, let's see, I think this is 2004, 2005, something like this. So, so Park-Taylor formula was 86. Now we're fast forwarding in time, but I think this is one of the, among other things, one of the nicest way of proving that formula. So the first important point is to think about the analytic structure of the amplitudes, of the and particularly of the color ordered partial amplitudes. So just take the particles in the natural ordering. So what's the, we just discussed a bit what the pole structure is. So again, these color ordered Feynman rules that I didn't give explicitly, but I kind of talked about them. They tell you that you basically need to draw ordinary Feynman diagrams. They look like the ones that you're used to, but you always draw them in a planar ordering. Right? So for instance, something like this. Could be more particles. So these are explicitly planar. So in particular, we don't have something where, say, I take this gluon, I put it over there, and I label it 3, and I say 1, 2, 3, 4. So that would be something non-planar. So, is that sufficiently clear, or do you want is it clear what I mean by planar in this sense? It's not clear? It's clear? Okay. All right. Rob?
So it's obviously not just a constant. Okay. Yeah, could you speak a bit more precise?
Yeah, sure, thank you. So let's say for the full Feynman diagrams. So if you, for instance, if you were to compute this, A twiddle, so this is the difference here. So this color order rules compute the A. But for A twiddle, let's say for 4 particles, for instance, I would have to. So what would I have? I'd define this diagram here. I would have its F, some F here, some F there, and so on. But then I'd also draw other diagrams where, let's say like so, something that one could call a U-channel diagram. So 1, 2, 3, 4. Well, in others as well. And so here the point is that this, from the point of view of singularities, this will have a singularity at P1 plus P2 squared equals 0. And so on the other hand, this diagram here, so here I joined 1 and 3, so there could be a singularity at this location, and so on. And now for these, so this is for a twiddle. But for the partial amplitudes, they can be computed from diagrams which are explicitly planar, where the only poles come from propagators, where the momentum that flows through is a sum of adjacent momenta. So for instance, for this one, P1 plus P2, and for this one, P1 plus P2 plus P3 plus P4, and so on. So this is this statement that I made up there. Does that help? Thanks. All right. So now the important thing to realize is that we know that the only poles are situated at these locations. On the other hand, the P-level amplitudes they are rational functions in the momenta or in the lambdas, lambda twiddles. And the idea is to use some complex analysis argument. So if you remember your school or let's say high school days, so if you have a rational function and you know about where its poles are, perhaps you also know what residues are, essentially you can reconstruct the function from that. And that's precisely the idea we'd like to use here. Now we've discussed a little bit where the poles are, so there's kind of 2 things that are missing. We need to discuss what are the residues. That's one thing. And the other thing is, well, in complex analysis, usually you have some complex variable, Z, or Z for the guys from the US. So where's the Z? So let's start by introducing this. And this is kind of interesting also in respect to this discussion we had earlier about the kinematics. Remember that the kinematics is still a little bit constrained, so we cannot just do anything we like. So this is actually quite interesting how one can introduce a parameter to do this complex analysis in. And this is known as the BCFW shift. BCFW shift. So let me define it. So I'll do it for 2. So one selects 2 particles I. In my case, I just choose I and N, but it could be in principle any of them. And I shift the lambda 1 spinner and the lambda tilde N spinner. in the following way. So for shifted quantities, I'll denote them by a hat. And so then what is this? So lambda 1 will go to lambda 1 minus z lambda n. And lambda twiddle n will go to lambda twiddle n plus z lambda 1 twiddle. Okay. So and in this z is a complex number. Well, this looks a bit strange. Let's see what does it actually mean in terms of the momenta. So if we put together lambda and lambda twiddle, let me just not write the indices. So so this to P1, it basically adds this piece z minus z lambda n lambda twiddle 1, and to Pn it adds the same piece but for plus sign. So first thing you see, okay, momentum conservation is still satisfied. So we have momentum conservation is okay because we have that the sum from 1 to n of the shifted momenta is still 0 as it should be. Simply this shift drops out between the two. Now the other thing we need to check is that the massless conditions are satisfied. So on shell conditions, are they also okay? Well, in a way, if you're a bit used to this spinelist formalism, it's actually obvious because the momenta they're factorized in some lambda piece and some lambda twiddle piece. And here, for each of the momenta, we just modified either the lambda or the lambda twiddle piece. But so, for instance, for P1, the on-shell condition is still satisfied simply because there's the lambda twiddle component. So this is in this sense it's obvious. This was just well, it's just thanks to the fact that we're using spins. Maybe here I just want to highlight really that this is so as soon as you sum, this we'll use later. As soon as you sum P1 hat and Pn hat, it's the same as P1 plus Pn. So for any, this is important to realize, for any sum of momenta that involve these two, they do not have any z dependence. So this will be important when you think about now what poles can we have in the Feynman diagrams as a function of z. So as soon as there's this sum P1 plus Pn hat, this is independent of z, and therefore there cannot be any poles. So this tells us that this is only special configurations will lead to any poles in z. This is what we'll think about now. One more comment. So I mentioned that z is a complex number, or we consider z to be a complex number. But certainly at this point, it's clear that we're no longer, in general, we're no longer considering real kinematics. So at this point, we've done a generalization, or we said we consider the amplitudes for complex values of a momenta. Might be a bit shocking, but on the other hand, if you think about complex analysis, it's quite standard to say, well, we have a function which initially is defined for real values, and then it can be quite profitable to look at what it does in the complex plane as well. So it's quite analogous of that. So where are the poles in Z of partial amplitudes?
Now you're considering this spectral amplitude is a function of n+1 complex variables, but what happened to the heuristics? So you're considering this as a function of...
So what we're doing here is for the moment it's independent of heuristics. In a way you can deal, we're not specifying any particular heuristics yet.
Okay.
We'll see later when we write down the relations, there will be, for some cases there will be simplifications, in particular this MHV case will be one of the simplest cases, but that will come in later. For the moment this is independent. Now you also asked about the number of variables that I didn't quite understand. Maybe I should emphasize here there's one parameter z that we introduced. So this is like, you can think of it as a generalized amplitude. So it depends on the original lambda and lambda tildes. And now we have one more parameter. We are actually interested in the amplitude for z equals 0. But it will be quite profitable to now analyze, can we relate it to the amplitude at z equals some other locations. Thank you. Right, so the next question is, where do the poles in z come from? So we, yes, and let's say that we denote this deformed amplitude A of z, poles in z of A of z. So I told you earlier that singularities can come from, in tree-level diagrams, they can come from propagators only. And moreover, for color-ordered amplitudes, the propagators, they always involve sums of neighboring momenta. So this is our starting point. So now we need to think what sums of neighboring momenta actually depend on z, and therefore can have a pole. And so the additional information we had is that if we sum P1 and Pn, even if they're shifted, z drops out. So we need some z dependence, so therefore we want either 1 or n to be involved in that sum. But if both of them are involved, that dependence drops out. Now, moreover, we have momentum conservation, so we can restrict ourselves to the case where we always eliminate n. So we can say we always look at the propagators which involve at least 1, right? And so since this basically leads us to the fact that we always have the only propagators that involve z are the ones which involve 1. And then go to some other number, let's say j. So, propagators that involve z are the following. So we need P1, and then we can sum this up to some j. So if you wish 1 over this would be the propagator. We cannot go further on this side because there we'd add Pn and then the z dependence drops out. Let me actually introduce some notation for that. So I want to call the propagator which goes from 1 to Pj minus 1. I want to define this as saying that this is the capital P j squared, so a shifted version of that. So capital J is P1 plus Pj minus 1. So this was the argument of the original propagator, and now it's been shifted, and for these objects we have a pole in Z. Now we can just compute what this is. So what is Pj Z at squared? Well, well, we can just separate this. So we have that P1 hat squared is 0 because it's on shell. So we just have P2 plus, and actually, sorry. So the best way is to decompose this into P1 plus, sorry, minus Z, so minus the shift, which is lambda n, lambda tilde 1. And so here we can reconstitute Pj, so we just have Pj squared. And then we have a term where we have minus Z, and we have lambda n, alpha, lambda 1 twiddle alpha dot, and Pj, let's call it beta dot, so epsilon alpha beta, epsilon alpha dot, beta dot, and there should be a 2. And so now I just like to use some notation for this. So similar to the square and angle brackets that we used earlier, I just denote this by the bracket n Pj 1 over here. So this is the argument of a shifted propagator. Now there's something very nice that you can see, namely that the dependence on Z is linear. This was a consequence of a masslessness condition. And so each such propagator, it will have a single pole in Z. And we know the location, so it's when this object vanishes. So the partial amplitude in general, it will have a single pole, a simple pole. So this shifted amplitude has a simple pole at this location Z. Let me call it Zj, which is defined as capital Pj squared divided by angle bracket n Pj 1. Now, what happens at this pole? Well, by construction now at this pole, this internal momentum here. This internal momentum squared is 0, so we can interpret this as some internal particle that goes on shell. So, at Zj, the internal momentum goes on shell. So if you think about the whole amplitude, and let me just try to write some sample Feynman diagram. Okay, so let's say we had 1 here, which is shifted. We have n here, which is also shifted. 2, 3, 4, 5. Okay. So here we could, for instance, look at this expression here. So this would, in my notation, let's see. So I guess this would be called P4 because we want to consider the sum up to 3. So P4. So this is P1 plus P2 plus P3. And so here there's so if we go to this value Z4 for shifted amplitude, then this means putting this propagator on shell. which sometimes people denote by a cut, but anyway, never mind that. It's just to denote that it's this pole that we're looking at. Now this picture is also it's kind of important to discuss it a bit more because it allows you to realize something. First of all, this was just a sample diagram, and there's many more Feynman diagrams to draw. And now you can think of the following. You can hold that line fixed, the line that you want to go on shell, and draw all color-ordered Feynman diagrams, or rather imagine drawing them, that would have such an internal line. And in doing so, then you complete all possible arrangements here of gluons on the left and all possible arrangements of gluons on the right. And you can convince yourself that in this way, by holding this line fixed, you generate actually all the diagrams that would contribute to some smaller amplitude here on the left, which has external particles 1, 2, 3, and this line here in the middle. And on the right, this line in the middle, and particles 4, 5, and so on, and n. So in other words, at the residue where the internal propagator goes on shell, we have a factorization into two lower point amplitudes, namely this left amplitude and the right amplitude. So this is very useful because it gives us a hint of, that's a basic idea for knowing what is the residue at that pole. Right? We need to do a little calculation what happens with the propagator if we take the residue, but then the rest is just regular expressions, and they're given by the sum of these Feynman diagrams on the left and on the right. So if we sum over all diagrams with this internal line, so with this 1 over p j line, so then we have a picture where we get the following picture, that we have an amplitude which we could call, let me call it the left amplitude, so which has this 1 here and so on, and whatever number of particles, and this would be j minus 1, in our example it was 3. Then we have the middle line, and then we have the amplitude on the right, and this starts with j and goes all the way up to n, which is also shifted. Are you happy so far? All right. Now, as always with such derivations, to do things right, one needs to go through some details, and I don't have the time to do that here. But what I told you is the rough picture. Now, to get everything right, one has to think a little bit more about what happens here with this internal line, and so it turns out that. There's a small difference between between the states out here and this internal line that I didn't tell you yet. So for the external states, we specified some helicity. I mean, I told you it didn't matter which it was, but they do have some definite helicity. But this internal line here, so far it's on shell, but I didn't tell you yet what the helicity degrees of freedom were. And but well, you can. I think it's well, one really has to go through the details, but I think you can. It's reasonable to what I'm just going to say, namely that when this internal particle goes on shell, then what you get here is actually a sum of all the possible helicity configurations for the internal line. So in fact, in this factorization formula here, there will be a sum over h, where h are the two possible internal helicity configuration. So this means that you could either have here a plus-minus helicity configuration or the minus-plus helicity configuration. So so then the full factorized formula, the full formula tells you that on this complex pole, you get a sum of helicities of the internal line, and what's then summed over is this product of the amplitude on the left and the amplitude on the right. And note, this is a bit unusual, these amplitudes on the left and on the right, they have still the shifted kinematics. So this is can be a bit confusing when you do a calculation for the first time, but it's quite important. So okay, this was a picture. Let me now just write down the formula. So let's put everything together. So we have this deformed amplitude, depends on our complex parameter z, and we discussed a bit how what poles it can have. So we have here a sum over the helicity of an internal line. We have an amplitude a left, which depends on this helicity, where we shifted particle 1, and we have particle 2. This goes up to j minus 1. And then we have this. We have now this on-shell momentum, which is evaluated at zj. I left a bit of space here by way to complete, but see about that. Another kind of technical detail, but important if you want to get the minuses and so on correct. This internal line, so we have some convention where all particles are outgoing. Now, of course, for the internal line, it will be outgoing for one amplitude and ingoing for the other one. So for one amplitude, we'll write this with the minus sign, and for the other one, with the plus sign. But, okay. So we have this, and then we have this a right, where this has then the opposite helicity. I'm just writing minus h. And so then this p zj as ingoing, particle j, and so on, until we arrive at n. Now, what else do we have? So what this kernel line means? So this is in the vicinity of z close to zj. There we have this pole. Now the one thing I've taken out is basically the propagator, which we analyzed up there. One can rewrite this a little bit, and then one can express what we had up there in terms of the values at j. So then you can just write this as z minus zj, so making very clear the pole in the complex plane. And then there's a little normalization factor, which is n j1. And okay, there might be an I here. Don't trust me on it. Right. Okay, so that's very important. That's in a way the main information we need to run our BCFW argument. Now, what's the idea? So now remember your complex analysis. So we are actually interested in the amplitude at 0, right? The Z was just a tool. And Well, how can we do it? Well, we could say it's this amplitude A of z. We multiply it by some pole. We artificially create a pole at 0, and we say now we integrate here around some contour C0, which encircles the origin. So what's this? The picture for that is just that we have our complex plane, and by considering AZ over Z, we have a pole at the origin, and well, we just take the contour integral, and this way we reproduce A0. And if you wish, so just to be exactly with some 2 pi I here, so everything is good. Now, we just saw that there's various poles in the complex plane as a function of Z, and various locations, complex locations in general Zj. So the idea now is to rewrite that integral in terms of, or rather that residue in terms of all the other residues in the complex plane, where we know exactly what the residue is thanks to this formula. So we just write this as minus the formula up there. Actually, let's just do the picture because it's easier. So this picture then is equivalent to minus taking just all the residues at these poles, just as a sum at the poles in the complex plane. So what's the upshot then? So if we take that idea and now use this formula here, and take the and also let's take the residue, then we get the following. So now there's a little algebra to do. You see, we have, in addition to this formula, we have this factor z. So when we take the residue at any of these locations zj, we will get another factor 1 over zj, and then there's just a little calculation to do with this 1 over zj and this factor here, and it turns out that there's a simple answer. I spare you the calculation, and I just give you the answer. So what you get is the following. We have a sum over j because we want to sum over all these residues. We have the sum of the helicity of the internal particles. And then essentially we have this A left, which depends on H. I'm just now abbreviating a little bit. So this depends on Z, J. And here we have this A right, H. Also depends still on ZJ. And this is minus H. And it turns out when you do this little algebra calculation that actually here in the middle you just find Pj squared. But now the unshifted momentum, right? I mean, the shifted momentum squared would be 0 by definition. Anyway, this is just the outcome. Okay. Any comments here? I skipped over something, so maybe someone wants to complain or point it out. Yes?
So what is the physical implementation of the residue vanishes at infinity?
Very good. So the question is, what about residues at infinity, and what is their physical interpretation? So I don't have a good answer to the second question, which it's your real question. The first question is, so in this step we actually assumed something and I assumed it without telling you, namely that there's no contribution from infinity. So as usual in complex analysis here, you need to analyze also how A of Z behaves at infinity. And what we did here is valid if the amplitude vanishes. So this is, we should say this, valid if A of Z goes to 0 as Z goes to infinity. I'll tell you later that this is actually justified for gluon amplitudes, at least if one is a little bit careful. However, if this is not true, one can still proceed. I mean, there's nothing wrong with the idea. The only question is what is the term at infinity, and that's really a question. To be honest, I don't have a good answer. I don't have an answer which is equally good as this nice physical factorization interpretation. Nonetheless, in some circumstances, it may be still useful to consider such recursion relations and try to get something out of them. Another idea is that sometimes one can modify this approach, and in a way we're discussing here one of the simplest BCFW shifts, and there's variants of this which are a bit more sophisticated, which may work, which may give a vanishing at infinity when other approaches do not. So about this vanishing, it's one can show that this is actually the case. So this is true. It depends on the helicity of the shifted legs. So if the shifted legs, shifted gluons, let's say, have the following helicity. So we shifted 1 and n. So in actually 3 cases this works out. So if the helicity is plus minus, the helicity is plus plus, or if the helicity is minus minus, then this is okay. Then one can show that A of Z behaves as 1 over Z of Z goes to infinity.
Is it 1 minus minus, but you don't have minus?
Oh, thank you. Don't know where that happens. So in these 3 cases, this is fine. Actually, in the first case, it's relatively, it's not so complicated to show. And if you're interested, I can give you a reference where the other 2 cases are discussed. On the other hand, for the minus plus case, it is not shown. Now, you might don't worry too much. It seems like it works sometimes, doesn't work other times. The point is that we're completely free to choose what this pair 1n is. So, in other words, for given helicity configuration, we can just choose 2 neighboring gluons which satisfy this criteria, and this is always possible. So, so from that point of view, this is not a real, not a big restriction. So the method is certainly applicable to all cases of gluon amplitudes. All right. So now, what else do I need to say? Well, let's look a bit at this formula, because there's something really nice about it. So on the left-hand side, we have an n-particle formula, n-particle amplitude, and the right-hand side, we have a product of things. But very importantly, each of the amplitudes on the right has fewer external gluons. So, well, this is just a bit of combinatorics, but basically, in the worst case, one of these amplitudes here will have n-1 external particles. So in other words, this is a formula which can be used recursively. So let's say you know at some stage the 4 gluon amplitudes. Let's say the 4 gluon version of this MHV formula. And you could just write down the terms of this recursion relation to get the 5 gluon formula, 6 gluon, and so on. In practice, you would at some point spot a pattern, and then you see you have a chance of deriving some results for n particles, where n is just some arbitrary number. So this clearly gives you some advantage over just using Feynman diagrams, where it's really hard to spot such patterns. The other comment is, and this kind of is implicit in what I just said, that these building blocks here, they're not just some, let's say, some artificial construct, something that helped you in the calculation. They're also physically relevant amplitudes. So you're directly working in a space of very sensible and nice objects. So if there's anything nice and simple about the final amplitudes, it will be already manifest here for the ingredients you use, and this you have a chance that then the simplicity is carries on to the next object that you calculate. In other words, this is a formalism where you don't have a lot of auxiliary objects which may be more complicated than the final answer that you wish to compute. All right, so now, so I wanted to give you a little homework, but I realized that to give you that homework, I basically need a few more minutes to define a next element, and this says 0 minutes.
How many can you do? 3 minutes or 5 minutes?
Well, I realize we've had 2 lectures. It's the first lecture series. I don't want to, overdo it, and it's also lunchtime. So I think we just postpone till tomorrow, and then we still have actually tomorrow, maybe in a calm moment if you wish. I think it's a really profitable exercise to use that and compute this all-n formula. But let's postpone that to tomorrow. So that, you can ask questions, but for now, let me just thank you for your attention.
So right now we are really at the end also of the question session, but if there is one quick question, maybe let's go for it.
Sure.
Is there a similar recursion story at loop level, or does this only work at tree?
Yeah, that's a great question. So the question is there a similar story at loop level? I hinted at this idea that many techniques from tree level actually do carry over. I can give you a longer answer and also in discussions later. The short answer is yes. These ideas are very useful also at loop level. So far have been implemented in a specific context at loop level, but a very important one. So this has been implemented for planar n equals force to Bang-Mills theory, where it has allowed really to obtain loop level integrands at a spectacular loop level, which I think just using would be completely unthinkable using normal techniques. I think, at least if I'm informed well from the website, I think there's one SAGEX project which has to do with loop recursion relations. But I don't know if that's, don't want to give away any secrets, but what I read was on the website. So yeah, thanks for that question.
Okay, maybe 1 second question.
1 second.
Is it necessary to perform this approach after color completion? I mean, it seems like only for planar diagram there we can talk about
Right.
But the core problem I submitted is about the topology of the tree diagram.
Yes.
We can make what happen, then it becomes disconnected to diagram, right? Yeah.
Right. So the question is was it important that we did this color decomposition to run the BCFW argument? The short answer is no. You could do the same for the full amplitude. It's a little bit, I would say it's a little bit less convenient because you kind of have to deal with several things at the same time. And the most obvious, where this becomes the most obvious is, I think, in this analysis of which terms actually contribute to a given BCFW shift. Thanks to the color decomposition, we could just restrict ourselves to a subset of poles. This was very useful. Just as some food for thought, here I presented a particular BCFW shift where we shifted 2 adjacent gluons. There's also a variant where you can just pick any gluons I and j to shift. And in this case, this also yields a valid BCFW shift. However, the difference is a bit similar to what we just discussed. In that case, you would simply get more contributing diagrams. Simply because when the gluons are adjacent, you could use this property that their sum is independent of z, and so therefore then a lot of terms just simply don't depend on z. If you put the shifted gluons elsewhere, then there's more subset of momenta that can contribute, where you can have poles in. So there's not one unique BCFW shift, and as a consequence, you also can potentially get many different BCFW formulas. So these are all valid, and I think it depends on the specific purpose which one is the right one to use.
Okay, you can keep asking Johannes questions during lunch and also while he's around, so don't hesitate to come and talk to him also in person. Let's thank him for the session.